Welcome back to the solid state lectures. In this video, I would like to talk about the Einstein model of heat capacity of solids. Before going to this, we can recap what we have learned about the Debye model of heat capacity. In Debye model, vibrations of all frequency below a certain cutoff frequency are allowed in the crystal. But in Einstein model, the difference is that all frequencies are not allowed, but all the vibrations have same frequency. Okay, the frequency of vibration are represented by delta function, delta omega minus omega 0. So this is the frequencies are represented by this thing. That means the frequencies are centered around omega 0 and it is very narrow. Okay. So therefore the density of states is given by d of omega is equal to n times delta of omega minus omega 0, where n is the total number of oscillators. N is the total number of oscillators. Oscillators means maybe atoms. Okay. We are considering the crystal to be one dimensional. Okay, we can extend the study to the three-dimensional crystal as well. Now, the total thermal energy, therefore, is given by U is equal to N is the number of oscillators, N times the mean occupation number into energy of an oscillator, H cross omega. So here actually omega 0 is the frequency of all oscillators according to Einstein model, but we are considering H cross omega. This omega 0 is omega only. Therefore, if we substitute the value of the mean occupation number, then the equation of U become U equal to N 1 by exponential H cross omega by kt minus 1. So this becomes n h cross omega divided by e raised to h cross omega by kt minus 1. Therefore, the heat capacity of crystal, heat capacity of solid is equal to the partial derivative of the total energy with respect to temperature at constant volume. So this becomes n h cross omega. This is a function of the denominator is a function of temperature. So the derivative will become minus 1 by e raised to h cross omega by kt minus 1 square into e raised to h cross omega by kt into minus h cross omega by kt square. So this is the derivative of this thing. We can simplify this thing. This is equal to kt square is there, h cross omega is there, h cross omega is there, minus get cancelled. So therefore this, so if we multiply k, we can write nk h cross omega by kt square exponential h cross omega by kt divided by exponential h cross omega by kt minus 1 the whole square. So this is the heat capacity of an one-dimensional crystal according to Einstein model. So in 3 dimension, we have to replace the n by 3n. So in all the dimensions there are n oscillators. So we can write in 3 dimension the heat capacity become 3nk h cross omega by kt e raised to h cross omega by kt divided by e raised to h cross omega by kt minus 1 whole square. So this is the heat capacity. If we substitute h cross omega by kt is equal to x, then heat capacity become 3nk x square e raised to x divided by e raised to x minus 1 square. So this is the heat capacity of a solid at any temperature T. So we have seen in the last class the Debye model of heat capacity. Today we have seen the Einstein model of heat capacity. So the main difference is in Debye model, all the continuous ranges frequencies are allowed up to the cutoff frequency. But in Einstein model, only a certain frequency is allowed. That means all the oscillators have same frequency omega 0. For that we have considered a delta function, delta of omega minus omega 0. You know, delta function is 0 when omega is not equal to omega 0. Now the special cases. So at high temperature. High temperature means the room temperature is considered as high temperature, 300 Kelvin. Okay. So at high temperature, what happens? This x is equal to h cross omega by kt. So this t is high, that means x is small. Therefore, what happens to this e raised to x is, can be written as 1 plus x. So we can neglect the higher order terms. Therefore, if we substitute this here in the expression of heat capacity, Cv is equal to 3nk x square e raised to x is e raised to x is 1 plus x. When x is very small, we can write it 1 divided by e raised to x minus 1 is 1 plus x minus 1 is x square. So therefore, this will be equal to 3nk. So which is same as the result in obtained in Debye model at high temperature. So that means this is the classical expression for heat capacity at high temperature. Classical value of heat capacity. Okay. So this is called a Dulong-Petit law. Dulong okay. Next is at a low temperature. At a low temperature, that means when T is small, x is large. Okay. So in this case, what happens? E raised to this Cv equal to 3nk x square e raised to x divided by e raised to x minus 1. So this e raised to x is a very large quantity. When x is large, e raised to x is large. Therefore, e raised to x minus 1 can be written as e raised to x only. So e raised to x square is e raised to x divided by e raised to x square is e raised to minus x. So this will be 3nk x square e raised to minus x. Okay. So at low temperature, the heat capacity exponentially decreases. At low temperature means x is large. When x is large, the heat capacity exponentially decreases. So we have discussed already the Einstein model of heat capacity, and also we have discussed the Debye model of heat capacity in the last lecture, and we have seen the special cases of the heat capacity, that means at low temperature and at a high temperature in all these two cases. So now we can draw a graph, or we can plot graphs for these two cases, the Debye model and Einstein model, in a single graph. So let me draw the graph here. In the x-axis, I take temperature. In the y-axis, I take heat capacity. Okay. First, we draw the Debye model. Debye model, we know at a low temperature, this is proportional to T cube. So it's a T cube graph at low temperature. Okay. As temperature increases, the graph deviates from this T cube, and this function form is discussed in the last class. Okay. At high temperature, that means at a high temperature, when temperature is very high, it tends to approach the maximum value, that is, this value is 3 n kb. Okay. And this is the Debye model. The Einstein model, at low temperature, the heat capacity is 3 nk x square e raised to minus x, exponentially decays at low temperature. That means x is large. Okay, when x is large, this exponential decays. So this graph will look like this, and at a high temperature, that means low x, it tends to approach the value of 3 nk. So at a high temperature, this is in very good agreement with the Dulong-Petit law. But the experimental value of heat capacity, this is experimental value of heat capacity. The experimental value of heat capacity at low temperature is in very good agreement with the Debye model. It does not obey the Einstein model at low temperature. These are the heat capacity of solids according to Debye and Einstein models.